sorry if I'm being repetitive, but it's a great honor to be here, and thank you all. And it's wonderful to win this with like Nicole and Muhammad. That's like paper that I really, really like. And I like our paper too, and I want to tell you why. So as Nicole said, those are like important questions, like that you want to know whether it's a unique stable matching, a small core or not. And you want to know that, like I'm trying to echo Al. I also took Al's class, and he's kind of talking about the process of redesigning the residency matching, national residency match, and kind of being asked all sort of important things, like they all know that the proposing side will have an advantage. Both sides start lobbying. Who will get to propose? Will the doctors get to propose? Will the hospitals? Does it matter? Does it not? That's an important thing to know. Can you tell both sides that they can report the preference truthfully? It's an important thing. Every doctor that goes through the match and talks to somebody who says, like, I know the algorithm, asks, like, oh, should I report my preference truthfully? Like, you want to be able to tell them, can they misreport their preferences? I think of it as a very practical concern. If you just think about like just evaluating markets, if some side can manipulate, how come those markets work well? Should we be worried? So I think those are really practical concerns we want to think about. And kind of before Nicole's paper, there's a bit of reasons to be concerned. Because if you go to the theory that we had before Nicole's paper, you go and you sort of look at the examples, the toy example that Nicole said. Like, it's really easy to see that it's possible to have multiple stable matchings. Even if you say, I'm going to have a large market, many, many people, simple exercise, write an example with as many agents as you want, still has a large core, like big differences. Not hard to do. So worst case, it's pretty bad, you know. You start thinking about, well, maybe I should look at the conditions. What are the conditions that will guarantee unique stable matching? They're very stringent. There are papers that kind of look at this and you kind of say, like, we never think that those conditions will be satisfied in practice. Those are really stringent conditions. And then there's papers by Pitel and some with Knut and Mutwani. And like they kind of do simulation, the equivalent of the simulations. I'll talk a bit about them. They also make you think that there's going to be a lot of stable matchings. So a lot of reasons to be concerned in theory. But when Al started redesigning the NLP and looked at the data and they did the simulations, they kind of said, like, well, in practice, stable matching are essentially unique. They're not exactly unique, but they're essentially unique. So here are the numbers from the Roth-Berenson paper. And you can see, so I need to give you context. There's 20,000 doctors going through this a year. So the number of people that can be affected by switching from doctor proposing to hospital proposing is 20 out of 20,000. So approximately nobody. The right answer to give somebody who's an NLP is like you cannot manipulate. Like it's 1 in 1,000 that you can move by a bit. Okay? So the right answer practically is like, no, the stable matching is essentially unique for all kind of practical purposes. But it's not exactly unique. So now we need a different kind of theory. We need a theory that can tell us it's approximately unique. Probably. Because we know that we can write examples where it's not, but in practice, it's kind of unique. And Nicole's paper does a kind of a fantastic job. It's kind of saying, like, look, the NLP has some features to it. It's not like your random example. It's a market with a lot of people. It's 20,000 people, and they have short lists. And if I take those features seriously and incorporate them into the model, maybe that's what the theory was missing. Maybe now I can get a different model that matches reality much better. Like, if you take those two things, it's approximately unique. Yeah? So I love that paper. That's great. But you still have some questions remaining, because, well, like you say, given those features, you get an approximately unique stable matching. What about in general? If we don't have shortlists, if we don't have as large of a market as an RMP, do you think that stable matching will be unique or not? Like you're gonna say, like the students in your class and you wanna match them with assignments or like win internships and you're gonna run this match. Should you worry about uniqueness in this market or not? You're advising somebody. And since then, we had some experience seeing some markets, like, some of them are documented in papers, some of them we know kind of casually talking to people. And it turns out that stable matching are generally unique. Like, there's kind of exceptions that I'll mention in a second, but in a couple of slides. But you talk to anybody, whether they do school choice or matching to internships, it doesn't matter whether you run woman or men proposing. And the proposing side gives you basically, essentially the same thing. Not exactly, but basically the same thing. So now we kind of have like the problem again. Like, we have a theory and we have the world, and we need to reconcile them with each other. Like, if we care, I care, but we can either change the theory or change the world. Well, changing the world requires talking to people. I don't like talking to people, so I just want to change the theory. Yeah. So we want to look back at the theory and say, what can we add to the theory? What can we change to get a theory that matches the empirical facts that we see? And what we end up doing is going back to this paper by Pitel, Knuth, and Utwani, that in some sense you can think of this as a good worst case to think about. They kind of say, let's take a very stylized but kind of reasonable model where there's a lot of preference heterogeneity, draw preference for each agent, completely IAD. Okay? Of course, it's not completely realistic, but if you think of like, top students and top hospitals, and like they have some growth, maybe between them, that's not a bad approximation. And in any case, that kind of captures the preference heterogeneity that kind of makes matching markets interesting. So some reason to think this is a reasonable model to work with. And what they found is that in that kind of market, the likely outcome is multiplicity of stable matching. Like, if you're the proposing side, if you're a woman and women are proposing, then you get your log n best match, best choice. So I'll give a numerical example in the next slide, but log n is pretty good if there's n people in the market. On the other hand, if you're on the opposite side, you get n of log n. Better than random, but not by that much. So if there's market with 40 men and 40 women, here's for the men. If the rank of the men, if the men propose is going to be 4, they're going to be matched to the 4th most preferred wife if like they get to propose. But if the other side gets to propose, they only get matched to the 10th most preferred wife. So quite a big difference. Okay? And that seems very different from what we see in the NMP and other places. So a lot of multiplicity here. So what am I going to change? Well, I'm going to add a vertical axis and change the number of men. Yeah? So maybe we took the number of men and the number of women to be exactly equal. Let's see what happens with the unequal. Yeah? So I'm going to keep a blue dot. That's when the men propose. And a red dot, that's when the women propose. We know that the men always do better when they propose, so the blue dots are always lower. And it kind of makes sense that if there's more men, you can also show that formally, more men should be worse for the men, right? More competition among men. So the red dots should be going up, the blue dots should be going up. So two dots that are very easy to add here is this one and this one. Like, if the men propose and there's less men, they improve. And they're already getting log n. You don't expect them to improve they can't really improve by that much more. So it's slightly lower. If the men don't propose, if the other side propose, and there's more of them, they do slightly worse than the bad day they did before. Huh? Two of them make sense. The really question now is what happens if I take the red dot, but the men get to propose, like go to the right and the men get to propose, or to the left. Now there's less men, but they don't get to propose. And now there's a tension. What matters more, whether you get to propose or whether you're on the short or the long side? And it turns out the only thing that matters is whether you're on the short or the long side. So the only place where the blue dot and the red dot are really significantly different in whether exactly equal. You go to an imbalance of even 1, and even just to a market of 40. We're not taking asymptotics here. I explicitly want to show you kind of simulations from a market of 40, saying like you don't need large markets here. Even from a market of 40, an imbalance of just 1 already practically means it's kind of like doesn't matter who proposes as long as there's not exactly the same number of men and women. And you can also show this for like the if you just care about the percent of people that have multiple stable matches. So what we kind of like formalize this result, it's kind of like we found this by doing simulations, kind of like that's the backstory. And then like it was a while to understand, hey, this is a pretty strong result. Again, like Nicole said, like this is something very strong. We should be able to prove it. Took a while, but we managed to show that in all stable matchings, basically if there's less men than women, even by just one, then men will always get something like their log n, women will get something like their n over log n, and it essentially, again, doesn't matter who proposes. Okay? You get an essentially unique stable matching. And we got some intuition out of this too. Kind of like, this is not exactly how we proved the result, but like the intuition that we got from this is really thinking like kind of Nicole in terms of like this unmatched woman kind of being like we think of this as, you can think of it as an outside option. So the way I kind of like to start is just think of buyers-sellers. Like there's just money with prices, sellers with unit supply, buyers with unit demand. If there's an equal number of them, the core, the set of equilibrium outcomes is really huge, because any price between value and cost will clear the market. That's kind of like, that's where bargaining must come into play. But if you just add even one extra buyer, and there's like beautiful experiments by Vernon Smith that kind of show this imbalance that happens in practice too. If you just add one extra buyer, the core shrinks completely. And an easy argument is like if you have an extra buyer that's, an extra seller that's now unmatched, the extra seller will accept any price of epsilon. So nobody should be willing to take a price of more than epsilon. That forces price to be essentially at cost. No? What happens in the matching market, you can think of the unmatched woman as an outside option as well. That kind of forces the man to be better off because everybody now has an option of going to this extra woman. Now, this logic doesn't work quite the same way because this woman is a random woman, not all the men like her. But it turns out that in the model that we consider in this matching market, there's so much connectivity. If you affect the allocation of one man, you affect the allocation of other men. Some men like her, those men must be matched to women they like a lot. That creates outside option for other men, and you can show that it percolates, and like the analysis would do, follows those kind of rejection chains. If I get a different woman, that it means somebody else gets the place, somebody else gets this place. And tracing those rejection chains is the way we prove this. And this was very stupid of me. At least I got some notice. OK, so we kind of like follow those rejection chains and show how this effect percolates. And the matching markets are kind of surprisingly competitive. That kind of even this one extra woman kind of has somewhat similar effect to this Bertrand markets. So we had a very long, kind of complex proof. Kai and Thomas have a much simpler proof. Like their entire paper is 6 pages. I think our proof is maybe 4 times this length, the length of their entire paper. They have a really nice, simple argument using like the building up on Nicole's and Muhammad's paper. So I think this logic is kind of useful. I'm happy you got it. I'm happy that there's a much simpler proof out there. And there's some other things that kind of we can also get from this kind of random models that kind of we also talk a bit about in the paper, like how it's not just that you get unique stable matching. We kind of get a characterization, understanding of the competition. That the men are really well off if they're on the short side, not so much in the other side. And you kind of compare it to how much they would get if they were just to choose women according to random serial dictatorship. So in terms of average rank, they do roughly as well. So it kind of seems really competitive in the sense like they get to choose. And it can kind of ask, well, is that kind of realistic again? Like, is this kind of a prediction? And like there's some follow-up, like beautiful work followed by Yash together with Pengyu and Senki. That kind of says, well, we can get more realistic versions of this if we kind of like change the parameters in the model, how long is the list, how kind of dense the market is, which you can also think of the market makers, things that you can affect. You can also use this kind of models to not just like kind of think of like, okay, do we get like the theory of small core, but can we actually give the right advice to people of whether people can manipulate or not? And we did a bunch of simulations and explorations for this paper, and like generally, I really think that any matching market that you're going to run is going to have a unique stable matching, and manipulation is not going to be an issue. But there are cases where it is, okay? And two kind of cases that like really worth mentioning is one, when you have like really large colleges. So Patak and Kojima show that if there's many, many small colleges, it's fine. But there's a beautiful paper by Eduardo Azevedo saying like if you have a few big colleges, they have market power, or the relevant version of market power here. There's a beautiful paper by Biros, Hasidim, Rom, Shorer, Savego that kind of says if colleges offer financial aid, and I know that if you're going to be rejected by my financial aid, you're still going to go to the college without financial aid. That's a form of local preferences for the college. It's not just a random two programs. It's two programs that are really related. That's a form of market power. That, again, brings the power of some manipulation. So it kind of like seems like competition in general markets. Like there's exception. Local market power can be a thing, even if markets are generally competitive. And I guess I should wrap up, right? So there's a lot of other kind of examples and a lot of other papers that kind of take random structures or different kind of modeling assumptions. Like matching with couples is another kind of like example where we know that it may not exist, but if we do the stochastic models, we can say when it's likely to exist. Many, many models where you can use those random structure to understand something about the market and ask a lot of interesting questions, like where should I invest? If I have a tie-breaking rule, how should I manage this? How should I manage a platform? A lot of those things are really useful when you have those random matching markets and you can uncover some structure that's really useful. So let me just wrap up, kind of say, like, we ran a ton of simulations and a lot of things in this paper, and I kind of think one thing that's convinced me, and hopefully convinces you, that like stable matching are essentially unique pretty generally, which means that manipulation is not really kind of an issue. That really needed a stochastic model, because the right answer here is that matching markets are approximately unique in probability. Okay? It's possible that they're not, but those are not the relevant situations. So we need kind of a model that will be able to say approximately in probability. So that's one of the personal takeaways. Like it's really important to work on those models. Sometimes the worst case analysis is really helpful. Sometimes it gives you the wrong answer. Not the relevant answer in practice, I should say. Not the wrong answer, just like not the practically relevant one. Simulations were super helpful, both to understand the result that we want to explain, and Nicole's kind of also said, like, Elle had simulations that inspired papers. I think that's great. We should be using simulations a ton. And the last thing is, like, a great advice is get great co-authors. It was really fun to work with Yash and Itai. I don't have pictures of them, but you can look at them. They're here. Okay. So thank you all. Thank you so much. Maybe
one quick question to Nicole or Jacob. Lunch is coming.
Thank you. Really nice talks by both of you. I was wondering, to what extent do the results require the preferences to be uniformly random?
So to what extent the results require the preference to be uniformly random? So for the proof, a lot. Because like the tractable analysis, we analyze a stochastic process that's similar to the process that Nicole described, without uniformly random, or IID mostly, we wouldn't have this kind of simple state to track, and that's very complicated. We ran a lot of simulations, and the structure that you can get can be very different if you have different correlation structure. And there's a paper by Liat that explores this too, and some paper by, I think, yeah, Liat and Sang-Mok Lee that explores different things. And like, interesting things happen when you allow for different correlations. The uniqueness of stable matching was something that we just, we couldn't break. We tried a bunch of things, and you had to go to something super convoluted, fine, that would also break once you play around with it. So uniqueness, I think, is better in general.